This is the first part of 2 or 3 sort of basic model rocketry workshops. For those of you who don't know me, my name is Jared. I'm a third-year EAN student at VEC. I'm also the president of Victoria Engineering Club. Before that, I was head of the VRAM team, which focused on robotics and mechatronics. And for part-time work, I also teach electronics programming and woodwork to some younger students, which is really fun and satisfying. I wanted to run these sort of workshops because I love rocketry. I think rocketry comes under the category of mechatronics once you start putting electronics in them, so I can make it a VRAM thing. And I wanted to see if I could do something fun and interesting to get a few more people involved with the Victoria Engineering Club space. So I'm glad to see we've got some cool faces turning out today. What we're going to be doing more or less in this sort of workshops is going over the real basics of model rockets, a little bit about the rules and regulations in New Zealand for running model rockets, and then looking at some stability and some CAD stuff, so how we can design parts for them, and a little bit about the stability of how a model rocket flies. From there, you could either then develop your own stuff, or I'm hoping to run some more advanced stuff with the engineering club in the future. This is going to be a multiple part thing. Today we're going to hopefully get some designs done in CAD, or maybe not quite finished today, but because the CAD's cloud-based, you guys can use it at home and then send me when you're done. And then I'm going to go away, get those 3D printed, get some stuff like these body tubes and parachutes and lines and all the good stuff that we actually use to build the thing out of, get some of that for each of you, and then we'll have another workshop where we actually build a little rocket, quite like the one I've got there. And then when we have a sunny, not windy day, so to be confirmed, go find somewhere where we can fly them. So when I was thinking about what to talk about, I thought about where do you start with model rocketry? What's the first thing you do if you want to get something off the ground? Well, you need to know what you're allowed to do. The New Zealand Rocketry Association has a whole bunch of different rules and things that limit what we can do, although these are actually really relaxed rules, which is nice. They define a couple of different classes of rocket. So a model rocket is really small stuff with motors in a class A to D. They have a large model rocket, which is higher impulse class motors and has a sort of weight limit associated with it. And then when you get into the really high power stuff, high power rockets, they have a lot more rules and regulations on what you're allowed to do and how you're allowed to do it, because you've got something big enough and fast enough that it could cause real harm if you're silly. The small stuff, you can just launch it at the park. You don't have to ask permission as long as the park you're launching it from doesn't mind. And if you go slightly bigger, you might have to talk to air traffic control just to tell them, hey, we're launching rockets here today. But other than that, they are very lenient on us. Although there will be safety requirements, which is like it has to have a parachute, and you can't put explosives in it. You know, point it at the sky, not at your neighbor's house, stuff like that. So we've talked about impulse classes in the categories. What is impulse? Well, impulse is basically the sum up of all of the force that your motor produces. To put it mathematically, it would be the thrust of the rocket, which is not a constant. It will have a differing thrust over the burn time, integrated with respect to time. But really, it's just the amount of energy it has, but not in respect to time. They're measured in Newton seconds, and so we'll be saying Newton seconds quite a lot when looking at different classes of motors. But basically, the more impulse you have, generally the faster and higher your rocket is going to go. We are going to be using primarily A and maybe some B class motors. The impulse class for the motors is basically just a way of grouping general performance. So an A is allowed to have 2.5 Newton seconds, and each letter you go up, it's double. So B is 5, C is 10, etc. And the NZRA uses that to determine some of our safety factors. So for A, B, C, and Ds, you can't have anyone standing closer than 5 meters to it when you light the fuse. For larger motors like E's and F's, they push that out to 10 meters. It also is used to define how big of a launch site you need, because if it goes up higher, it's probably a larger area where it could end up landing. You need to make sure you have a larger area where it's not going to fall on someone. For A's and B's, they're not going to go very high, so it's 30 and 60 meters. It's not too big. Even Kelburn Park down the road is theoretically big enough that we could do that. I'm not sure if anyone like the Wines and Cable car next door would be too happy with us doing that, but that's one of the launch sites I'm looking at for later on. This is what these motors look like. They come in a little pack like this. You've got a couple motors in there. It'll also have some of the igniters for them, which is really nice. I actually have one that I have used here with me. If you guys want, you can pass this all around and look at it. They are very basic. It's a cardboard tube, a little ceramic nozzle, and it's filled with black powder. Yeah, this is pretty much the same as the Chinese were doing it in the 1500s, but it works. It's easy to ignite, it's light, it's cheap. The Middle Ages might want their materials back, but for us, it does the job. They will have some numbers printed on the side. What do these numbers mean? Well, this one is an A83. The A is the impulse class. It is an A, it has 2.5 Newton seconds. The 8 is its average thrust, and the 3 is the parachute delay, which I will get to. You can get bigger motors like a C6-7 or an E16-6. But hang on, if you think about those numbers, does that actually make sense? Why does the A have more thrust than the C? And why does the C have a longer parachute delay than the E? And who chose purple for the E? I didn't have anything else to point out for that one. Well, this is because of the different intended uses for these different motors. An A83 is really a baby's first rocket motor. Its flight profile that it's looking at is going to be really quite safe and quite easy. Something like the C, and especially the C6-7, is looking at taking a lightweight rocket and going quite high with it, whereas the E16 is much more about a much bigger, heavier rocket. The A8, if we look at these graphs, you can really see the difference. So the colors didn't line up. I couldn't choose the colors for this graph because it comes from a very helpful website called thrustcurve.org, where they've got thrust curves for almost every different model rocket you can get your hands on. And oftentimes the label at the back of the rocket doesn't tell you this, so you can look at what you're going to get before you buy it and get a motor that's going to do what you actually want. So in red, we've got the A8, and you can see it's got quite a big spike, and then it tails off for a bit, and it doesn't have a very long burn time at all, just over half a second. This is because when you're launching the rocket, they're stabilized aerodynamically, but it has to be moving through the air for the air to do any work stabilizing it. And before it does that, it's going to be on a launch rod, but that's only like this long. So it's got to get up to a speed where it's going to be able to aerodynamically stabilize itself in about this much room, which is not very much. So you need to have a bit of a kick to get it going fast early, and then you can tail off the thrust a bit to limit how fast it ends up going. The C6-7 burns for a really, really long time, 2 seconds. 2 seconds with 10 Newton seconds of impulse is a lot of burn time. That means that it doesn't have a lot of thrust. So you can't really lift a very heavy rocket with 5 newtons of thrust, but if you've got something light, you can really lift it for a long time. You're going to be accelerating consistently at a low rate over a long time. You're not going to get super fast, but that means you're not having to deal with a lot of drag. That is the biggest motor I intend on running in this rocket, and that would probably get it close to 200 to 300 meters of altitude. So something really lightweight, you can get quite a long way with that. And then we've just got the E, which has a lot more thrust for about the same time. So, and these are, more zoomed in graphs of the same things. So really short burn time on the A8, much longer on the C. The peak thrust is quite similar, and the sustained thrust is quite similar, but the C just has more for longer. And that really shows how you can use the different motors to do different things. So hey guys, parachute delay. That's the next thing to think about. That's the next number on the side of our motor. You don't want to open the parachute when the rocket's moving fast. That's how you rip your rocket in half. You want to be opening the parachute right at the top of the arc where the rocket is going the slowest. In order to do that, we have a parachute delay. The way these open, the way the parachute actually comes out, is literally there is an explosive charge on top of the motor with a delay, and it pops the nose off, and the parachute comes out. It is quite low tech. It's literally, you've got your motor, and then a little bit of delay, and then a bit more black powder that pops it out, and then you have a parachute. Not very complicated, but it gets the job done. You want this to happen at just the right time. and they will make the same motors with different delays for different applications. So you'll probably, we've got a bit of simulation software we can look at, and that'll let you see, it'll come up with an approximate parachute delay that it thinks your rocket's going to want, and then you try and buy the motor that is closest to that. It might not get it spot on, but as long as you're not popping open the parachute too early or too late by a lot, you're probably not going to rip your rocket in half. Otherwise, maybe you get a different motor. So what are we actually going to do? Well, a big part of this is going to be 3D printing and designing our own parts for 3D printing. This is the one I built as a prototype for this very course, and I've 3D printed the nose cone section for it, and I've also 3D printed this tail section that just friction fits in there. It has the fins on it for stability, and it also has all of the relevant hardware for holding onto the rocket motor. For purposes of time, we're not going to be designing the core of the fin can. I'm just going to be having you guys design some fins for it. That means that you don't have to worry about all of the very tight tolerances and stuff like the launch lug adapter and all that. But the nose cone, that's going to be all you guys. And so yeah, here is a 3D model of this exact rocket. And so you can see the main different parts that it split into when I've done it this way. Now, the more traditional way to do a model rocket with less 3D printing would be buying a nose cone, you'd be buying the same body tube and parachute, and your motor is going to be held in by a cardboard tube with some spacer rings inside the body tube. That requires some gluing and some spacers and some cardboard and stuff. It's not too hard to do, but since we're 3D printing fins anyway, I've decided to do one solid piece that contains everything, and I actually found that this is competitive in terms of weight. It's definitely stronger, and it's, in my opinion, a lot easier. And so what are we going to do for CAD? Well, if anyone here already has some CAD experience, feel free to use whatever software you would like. For this workshop, I'm going to be mostly working with Onshape. Onshape is free, and it's not just free for students like Fusion 360. You can use the free version, or if you want to, you can sign up for the education version. The main difference is the public free version doesn't let your files be private, which is a little annoying, but it's not a complete deal breaker for everyone. But we're all students here, so we can go with the education version too. I did not find it was difficult to sign up for that. It's quite an easy to learn, quite an easy to get a hang of system. And it's cloud-based, so it's really easy to go from my laptop to my desktop or any other computer, and it actually has a really good built-in version tracking system. So I've been able to branch my part I've been designing to try different size fins, or even keep the version without any fins at all. It works on the same way that Fusion 360 or SolidWorks work. It uses the same system. So it can also be a really good stepping stone to jump up to the more advanced ones that you might want to use for bigger projects or see being used in other courses or in industry. Okay, and we have a couple of requirements for the nose cone, which is where we're going to start with. And I'll probably leave that slide up when we're doing things, but I'll be doing a demo as well, so don't worry. But this is because the nose cone basically just needs to friction fit into the body tube. We could try do something more fancy to hold it together, but this is just kind of the standard for rocketry at this scale, and it is more than enough. The body tube we're using is called a BT50. That's just a name for basically what is a 25mm tube of lightweight cardboard construction. It has a 24.8mm outer diameter, and it is 0.4mm thick, so we have a 24mm inner diameter. We want the outer diameter of the nose cone to be exactly the same as the inner diameter of the body tube so that they have a fair bit of friction. I've actually taken a single layer of tape to put around mine just to make that friction fit a little bit more. So there's a little bit of tolerance in there for things to be not quite right. We can always adjust it with tape later, but we're going to aim for 24 on that outside surface. And then general 3D printing sizes advice. We don't really want to make anything smaller than 1mm. My fins on this version were really pushing that limit. These are 0.8. Anything about 1mm in diameter is going to be fine. Thicker than that, 1.5 or 2 is probably going to be recommended. It's going to be just that little bit stronger. but you don't really want to start making things much thinner than 1 millimeter. Depending on, that does depend on your printer, but the stuff we've got access to, surfaces smaller than 1 millimeter are going to be a little sketchy. And then the length of the coupler itself should be about 10 millimeters at least, maybe longer. That's so that when it's sitting in here, it isn't wobbling around. If it's too short, there isn't enough surface and it can just kind of wobble its way out. You want it to be long enough that it's actually going to be stabilized by the tube. It's not going to try and kink the tube if there's a side force pushing on it. It's not just going to go, yeah. So it needs to be long enough, but we don't want to be making it too unnecessarily long, because if it's too long, we're just adding extra weight for the sake of it. And then it needs to have a way of attaching to everything else. As you can see, everything's actually just kind of held together by some lines. It needs to have a hole on it so that we can attach these lines to it. I would say a 2.5 millimeter diameter is about what we'd want to use for that. And the hole can really just kind of be mounted anywhere. As long as there's somewhere we can tie some shock cord on, we're going to be fine. And other than that, this is kind of, I would like to see people come up with whatever they want, really. You could try come up with something really aerodynamic and sensible, or you can try do something fun and a little more different. We're going to try and launch these, but I don't mind if there are some crazy designs that may or may not be stable. That's just more fun. As long as it's vaguely pointy shaped and looks cool, I'm happy. It can be hollow or it can be solid. Mass at the nose cone isn't actually a bad thing. Having a heavier nose cone is actually going to help your stability. Less mass obviously means rocket go higher, but having more mass at the nose is going to make up for having more mass at the back, which we'll talk about stability later on. The next thing I'm planning on doing is doing a little demo of basic on-shape stuff. But before I get into that, does anyone have any questions or comments I'd like to make? No? Okay, that's easy. So, this is what it looks like when you have logged into Onshape. I have a whole bunch of different things I've already made and worked on. If you guys want, while I'm talking about this, you can start making an account or something like that. And what I'm going to be doing is just making a new document. And it's going to make me re-log in again because I only logged in last night. Is it going to work this time? It is going to work this time. Fantastic. So, a thing about Onshape and Fusion 360/SolidWorks, for those who haven't used it much yet, is they work a little bit differently to how some more basic CAD programs work. I used to do a lot of stuff with Tinkercad because I learned it at a different course from a different education provider, and it is very basic and quite limiting, but really easy to get the hang of because you just get shapes. If you want a cube, you just grab a cube. If you want a sphere, you grab a sphere. If you want a cone, you grab a cone. It's a three-dimensional base that you begin with. SolidWorks, Fusion 360, Onshape, that is not what they do. The way this works is that you start with two-dimensional sketches, and you then extrapolate those into 3 dimensions via various systems. So it takes a little bit of time to wrap your head around how it actually works, because you're not starting with something 3-dimensional, you're starting with something 2-dimensional and then using that to make something 3-dimensional. So if I wanted to just make a basic cube, I'm going to make a sketch. Now it's going to ask me to pick a plane to make the sketch on. So I can either have the sketch being on the top plane, and then I'll be working in the X and Y directions, and I'm going to be extrapolating that into 3D on the Z dimension. So if I click on that, I can start the sketch. And if you can go back into it the side. So the sketch is on this axis here. And then I can zoom in. This is the origin point. If you want something to be referenced around a consistent point, I like to use the origin so you can measure stuff from it. And then I'm just going to take a square tool and I'll make a square. Now, the thing with this is that you don't actually have to get the dimensions right first click. You probably won't, and you don't really need to either, because of this tool up here where it says dimension. This is a very, very useful tool, because what it allows you to do is put these little annotations on, essentially, that have the size of it. The default is in millimeters, by the way. Now, the thing is that you can change that number, and it will update the size of what it is. So this isn't actually telling you what size it is. This is specifying what size it is. So if I make that 24, it's going to adjust it a little bit. If I then double click it again and make it 240, it's going to change the size of the part to match that number. So I can basically decide exactly what I want this to be by doing this. And the cool thing about it is that you can go back and change stuff without changing what you did afterwards, and it'll update it. So let's leave it like this. I'll make it 25 by 20, and then I'm going to click over here to finish that sketch. So I've now got a little rectangle on the X and Y plane, and I'm going to take the extrude tool. I'm going to click on its surface, and I can then make it into a cube by doing this. Now, let's say I changed my mind and I didn't want it to be the size that it was. I can go back into my sketch. I can take this side, which was 20. I can make it 40. It'll update the sketch. I select that I'm done, and it's updated the extrude. So your sketch is defining the three-dimensional shape, and you can change the sketches, which will then change what you did to them afterwards. So you can make something that you don't know the exact dimensions and then come back and update them later. Or you can, if you have to redesign something, you can get back into it and change what you did before to make it fit what's happened afterwards. This is pretty common for these types of CAD tools. SolidWorks does it, Fusion 360 does it too. It's pretty normal. The difference I found with Onshape is it's really intuitive how it works. I haven't spent as much time with the more advanced CAD software, but what I have done with this, I found that it is really quite easy to get a hang of, so I figured that's what we could use today. So for making a nose cone, see, if you delete it, it's just going to say I don't have the thing that I'm referenced to anymore. To make a nose cone, we are going to use the second tool here, which is revolve, because we want something, well, if you want to make one that looks more like this, we want something that has a fairly complex curved shape. Now, there are tools to sketch curved lines, but if you can't get a curve from a circle, you have to start the other side. So instead of working from the top down, I'm going to work on this plane in the sketch. And the first thing is we need to have the part for the coupler that is going to be flat and has very specific dimensions. So we had a 24 millimeter outer diameter. So I'm just going to make that line, and then we had another line vertical to it. And then it probably goes out a little bit more to make up for the dimension of the cardboard tube. So I've got these 4 lines already, and you can just quickly add them in and then come back along and actually dimension them to what they really need to be rather than just what you quickly did on the first try. So I wanted an exactly 12 millimeter radius to fit snugly inside the cardboard tube. I don't need this to be, well, I'll make it a little bit longer than 10 millimeters for a safety factor, so I'll call that 15. The wall thickness of my cardboard tube is 0.4 millimeters, and so if I have this little step out, that's going to mean that the section after the cardboard tube is going to be perfectly flush with its outside. We won't have a little step creating drag. And then I'll just have a nice little 2 millimeter section up top before we get into the curve part. And then I can make another line here where I'm going to say I want the nose cone overall to be, I don't know, 60 millimeters long. That sounds like a reasonable number, and I'll do that. And then I can grab a, which arc tool should we use? I'm going to try this one, and then I'm going to just connect this point to this point. And that's actually probably not the right one because I had to connect a third point to it. So I can, if you hit escape, it lets you do this. And now I can, nope, actually that's the wrong tool. Cancel that. Will that let me change its shape? Will let me change its shape. Never mind. So I'll delete this little guy. So I use this tool here, the spline, and then by making it basically in a straight line and pressing escape to get out of the editing function, I now have these little points that I can use to manipulate the shape of it like so. So I can then do this. And then what I'm going to do is I now have that two-dimensional sketch of the cross section of my nose cone. I can select this. I can select the revolve tool. And I'm going to be revolving it around this axis here. Actually, okay, it doesn't like me doing it quite like that. I might have to make another sketch, which is just going to be a vertical line for it to revolve around. If I hide this one, I can see what I'm working on. And I can just make a little vertical line like that. Now I can unhide this one, revolve this around. Come on, let me do what I want to do. There we go. And so now what it's done is taken that cross section and it has spun it around the line that we selected, and I have something that looks vaguely nose cone like. And this is now going to be a 24mm circle. You can see it in the bottom here, which is exactly the size we needed to fit snugly into the tube. So that is sort of the basics of how we can do this. And basically what I want, or what you guys can do now, is have a go. Experiment with it, make something. I'm going to be walking around, having a look, offering help as needed. And we'll spend a little while working on a nose cone type thing. Anyone got questions or comments or anything? Anyone need help getting an on-shape sorted out? Yes, I can. That is a great suggestion. Thank you. So the big thing to remember is really just that 24mm outer diameter. That's going to have us fitting into the tube really nicely. And if you want to get a feel for what it actually is physically in real life, you feel free to come up and have a look at these. We've also got the various cords that we're going to use to actually hold it together as well. And I've got the rocket as well that you can have a look at too. And what I'll also do briefly is I'm going to quickly redesign what I had to show how you could also do it to make it a hollow nose cone instead of a solid one. So I'm going to go back and reopen the sketch, which is where I'll be pulling the three-dimensional profile out of by rotating the sketch. And then what you can do is if you make another set of lines on the interior of your setup, what that'll mean is that you can have, instead of the entire surface, you would just have the profile of the outside, and you are then rotating and revolving that instead of the entire thickness. So I can make a couple lines like that, and then I'm going to take my little curve tool again, and I'm going to bring that up to near the top of the nose cone. And I'm going to hit escape to cancel it out before I start rotating it beforehand. And I'm going to finish that up with a little line. And that means I can delete this line. And now I can go through and redimension these to have it be a nice thin wall. Remember, we don't want to go too thin on the walls because then we're going to be running into problems 3D printing it. So if I'm going to make that 2mm so that it's not too weak. So it looks like there are a couple people who are progressing with the design. And so what I'm going to do is basically show a little bit more about what we can continue to do in order to add other parts to what we've done. So if I wanted to add, say, oh, that's not as hollow as I thought it was going to be. If we want to add other parts onto the rocket, what we can't do is add them in places where the surface is curved. We can't draw on a curved surface, unfortunately. And what that means is that we need somewhere to add a flat surface. I'm just reprofiling this so that it's hollow to be a better example. So I can't draw on the inside of this face, like it won't let me sketch on it. And a sketch has to have a reference face that can either be one of the three main axes, or if we hide all of those, we can draw onto the faces of the rocket. So I could select this face and go sketch, and I can now draw on this surface, and I've still got this origin point here to use as a relative center. So if I want something to be perfectly centered and perfectly parallel, I've got this point there, and that line is now centered to the middle, and it is on a perfect 90 degrees. Is it actually on a perfect 90 degrees? I think I missed a bit. Nope, that is on a nice perfect axis there. And I can then use this to add another face to the bottom. So I can take it back and then out and down on the parallel. And so we've got a little square there. And for symmetry's sake, I can do the same thing on the other side. And then I can take my dimensions and make sure everything is the same dimensions. You can also dimension from points. So if I take this point and this point, I can dimension between these 2 points to specify how far out that goes. So if I want to have a 2.5 millimeter hole for the parachute line, that's going to need to be more than 2.5 millimeters long. So we've still got some plastic there to support it. So I'm going to say 4. That'll pull that out, and then I can make each one of these 2 so that I'll have plenty of room for the hole. And now I've got these 2 faces here, and I can select them, and it would extrude out that way by default, but I can change the direction. I don't need it to be 25 millimeters thick. I probably only need, I don't know, 4. And it is going new versus add. If I make it new, this will be a separate part. If I go add, this will be added into the same part as the rest of it. And then I've got this little block. And I can now then make another sketch on its face, or I could edit that sketch that I had there before. And if I add a circle to it, for example, it's got a little trace line for the middle point. I can make a circle. I can specify the diameter of that circle. And then you see, it got moved because I don't have it referenced on a line or anything. But to keep this quick so you guys can get back to it, once you have that, you can then take the same extrude tool, but instead of adding, I can remove. So this is how you would make a hole. I wouldn't recommend making a hole right in the side of the rocket. This is not great for its integrity. You just need to have that reference to something to stop it from pulling it to the edge, basically. So that's how we can add more material to something and then take it away to make holes. I've seen people making some pretty good progress. We have a little bit less than half an hour to go now. So what I might do is just do the rest of the presentation, which is going to talk a bit about rocket stability and fins and stuff like that. And then you guys can continue with making your 3D models at home over the weekend and stuff like that. So I will also mention for when we are assembling these, I will basically need enough time to get everything 3D printed and also to have enough things like body tubes ordered and delivered from the supplier in Auckland. So I'm hoping to be able to get that done in 2 weeks, but that might end up being 3. So I know people are going to be quite busy in week 5 and week 6. It may even end up being part of the mid-tribe break if that's easier for people, but things might get pushed back depending on how long it takes to get everything 3D printed. I don't know how busy the place I take 3D printing is going to be, so we could be looking at a couple weeks there. What I'll do is I'll put links on the VEC Discord server. Everyone's got access to that, right? Of somewhere where you can put the files, and also where you can get my design for the fin can and the motor holder, basically the part at the bottom of the rocket that holds the motor in and gives us a place to attach the fins to. I designed all the hardware to hold the motor in just because that needs to have some very specific dimensions, and rather than make you guys have to make precisely sized cylinders, I thought it'd be more interesting to let you guys focus on making fins. So, after we've done that and we've done the demo, rocket stability. How do rockets be stable? So a really important thing there is the relationship between two theoretical centers. The center of the rocket's mass, or its center of gravity, and the center of the rocket's pressure, or where all of its drag is concentrated around. These images from NASA illustrate nicely where you want these things to be. You want the center of pressure to be behind the center of gravity. Otherwise, it is going to be very unstable. So this is what OpenRocket looks like, which is a rocket simulation software that we might explore in a future workshop. The circle with the quarter circle markers is the center of mass, and the circle with the smaller circle inside it is the center of pressure. As you can imagine, if your center of pressure is behind your center of mass, it is going to be correcting it. So when your drag is acting through here and your mass is acting through here, this force is going to do that. Whereas if it's the other way, when you get an angle, if your drag is acting through here, it's going to make it worse rather than making it better. How do the professionals control their stability of their rockets? Most orbital launch vehicles these days don't have massive fins hanging off the side of them. You can use movable fins for flight control, but a lot of the time they do it with vectoring thrust, either gimbaling the entire rocket nozzle, or having little vernier rockets, or having thrust vanes. And using thrust can give you a lot of advantages for rocket control. But for us to do that would be really, really hard, and we needed a lot of electronics. And I want to do it later on anyway, but not for the first time. Instead, we're going to have passive fins. And this brings us to a free body diagram. And I'm going to do a very quick, very basic explanation of this, because not all of us are physicists and not all of us need the super advanced version. And also my physics is probably a little rusty, so I hope I don't get this wrong. But if we look at an aeroplane, for example, we see that there are different forces acting on it, and they all are acting through its theoretical center of mass. So it's got thrust from the engines going in one direction, and drag and weight and lift all acting on it in different directions. And if the sum of all these forces on their vectors all cancels out to zero, it will continue doing whatever it is doing. It will not accelerate or decelerate or go up or go down if all the forces are balanced. If they are not balanced, then it will do something. That might be fall out of the sky, or it might be climb, or it might be go faster, or it might be slow down. And a very simplified rocket is just a tube. And if we have the force of gravity pulling it down and its own thrust pushing it up, it's going to either go at a constant speed, or if it has enough thrust, it's going to be accelerating. But if we have something like the wind push on it at the top, it is going to want to rotate around its center of mass. And then what happens is it spins. And that is not great, because if it's spinning around like that, you are probably not going to go very high. So instead, we can add some fins onto it. And when it has been knocked over by something, these fins are now going to be, especially the ones on these angles, maybe not this one at this angle, but these fins are now going to be interacting more with the airstream. And they're going to create a force that is normal or perpendicular to their axis, and that is going to create a force that is wanting to rotate the rocket in another direction. Or you could call that a torque, because it's going to be a rotational force, not a linear force. I just put this in here to clarify some physics stuff, but we probably don't need to worry about forces versus torques too much. So fins versus wings. A lot of rocketry stuff you'll see on the internet, they are just using flat profile fins with a little chamfer so that you're not dragging a straight edge through the airstream. Because if that was flattened off at the top, that's going to make quite a lot of drag. You could also do wings, for example. But a aeroplane-like profile on a wing is actually going to be creating a lifting force without having much of an angle on it, which is then when we can use what is called a laminar profile wing, which is a symmetrical wing, but it still has a curve on it. And a laminar flow wing isn't going to create any lifting force one way or another until it has an angle of attack relative to its airflow on that fin. So if we tilt these away, like if the rocket is starting to go sideways, there is now an angle relative to, because it's still going up, but it's being tilted. These fins now have an angle relative to the airflow, which means they're either going to create some drag or some lift in the direction that we want to stabilize it. Our rocket's going to be more stable if we have more force coming from those fins acting to right it back up again. Now, how do we calculate that? Well, that's the equation for drag, the force of drag, and that is kind of disgusting. Especially for an engineer, it's disgusting. You physicists love this, but for engineers, we don't want all that. That's too much. What can we get rid of that doesn't matter? And what is all this? Well, we've got a constant out front, we've got the density of air, we've got the velocity squared, so speed matters a lot. We've got the coefficient of drag, which is basically just like, what shape it is. And then we have the area, the cross-sectional area, how big it is. How much of this can we get rid of in order to actually use these variables to help us design a fin? Well, the constant we can't change. We can't use that to design something. We can't really use the density to design something. We might have to take it into consideration if we're going to go really high, but we can't change that to affect our design. We can't really change the velocity to affect our design. That's a rocket motor problem. So really, the things that we can change is the coefficient of drag and the area of the fins. So we can say that the force of drag is proportional to the shape of our fins and how big they are. Yes?
What about the number of?
That is basically just area. So I did 3 on this one for lightness, but this means that they're all a little bit off axis. So if it's kind of flying like this, these fins aren't each perfectly contributing to this angle. So you might need bigger fins if you have less of them. And conveniently, lift, the formula and equation for lift is actually very similar to the formula and equation for drag. We're just going to swap the coefficient of drag for the coefficient of lift. So basically, for designing fins, I think I need to go back some slides. For designing fins, a bigger fin is going to mean more force to try and restore our course, and the more force is going to mean more torque, so it's going to more aggressively try and be more stable. But adding bigger fins or fins with a more aggressive shape is going to add more drag and more weight. We could put some wing shapes. These have a wing shape on them, but we would have to then, if we wanted to do it properly, do some complicated math to work out our coefficients of lift, and that's painful, and I don't want to do that. And unless we want it to constantly spin, it's going to need to be a laminar flow design, so you can't just copy an aerofoil wing from an aeroplane. So it's a little bit more thinking we'd have to do. You can do that. I'm perfectly happy if you guys wanted to make some wing profiles. You could guess and check. You could try and find out how to do the math, but I'm certainly not going to be teaching you how to do that today. But basically, bigger fins, and a more aggressive profile is going to make the rocket more stable. So how do we know if it's stable? Well, we can simulate it. There is a nice little program called OpenRocket, which has a very 90s user interface, but it gets the job done. However, I don't think we have time to do that today, and that will be something we need to download and install. So again, we're not going to be simulating it today. But that doesn't matter, because even if the rocket comes out as unstable when you do simulate it after building it, you can fix it. I added 3 grams of blue tack to my nose cone, and that dramatically improved the stability of my rocket design. And it did that by moving the center of mass. We want the center of pressure to be behind the center of mass, like I mentioned earlier. If it's behind the center of mass, when we have a force created by the fins, it's acting behind where the mass is, and it'll straighten it up. If we had that force in front of it, it's going to make it worse, not better. So you don't want fins on your nose cone, you want fins at the back. The further away your center of pressure is from your center of mass, the more stable it's going to be. If you can get your center of mass close to the front of the rocket and the center of pressure close to the back, it's going to be very, very stable. You might need either really, really big fins to do that or a really, really big counterweight at the nose. The closer these two things are together, the less stable it's going to be. You might need bigger fins to make up for them being close together, or you might need to add some weight to the nose, and that's probably the direction we're going to go with. And then if you get to the point where they are reversed, that is not going to be a stable rocket, not at all. Which might be interesting to watch, but I wouldn't want to be standing too close to it. So this is the little design I came up with for holding the motor in place and also providing somewhere to attach parachute to, and also going to fit onto the launch rail. Because I mentioned this at the start, but these fins don't do anything until the rocket is moving. And the rocket is not moving when you light the motor. And that's why some of the motors have quite a high thrust for the first half a second or less, to get it moving fast enough while it's on the rail so that when it comes off the rail, the fins are going to be enough to keep it stable. So that we have that little section up top that just slides over the rail so that it can smoothly slide on up. The way we get the motor in and out of this design is literally with some little screws, and there are little captive nuts inside of it too. So I've taken care of all that. You guys don't need to worry about all the dimensions and looking up the dimensions of an M3 nut and then double checking that 3 times because you were still learning how to use the software and you didn't do it efficiently. You had to do the same thing 3 times over. You don't have to worry about that. So what we need to do though to make a fin is we need something flat that we can draw on. Unless you already know more than me about how to do this and have figured out how to draw on curved surfaces, we need a flat surface. So what I've done here is I've created another sketch on basically on this little lip going around the outside of the coupler section. This is like the same lip that we had on the nose cone where the body tube lines up flush with the outside edge. I've basically pulled the line across from the origin so that I know that I've made it on a straight line. And then I've taken these little lines up and across, and it's basically made a little triangle in there that is a flat surface. And then we can use this little tool up the top there. I don't know what it's called offhand, but that lets you select a drawing that you've made and then repeat that symmetrically around an arc a certain number of times. I picked 4 for this example, and you can see that it has replicated it at different spaces around the rocket. Now, if you are going to do this and you are going to do a number like 4, make sure you don't do what I did and have it lined up with the launch lug. Because if you have a fin in the way of that, the rail's not going to go through that. So you can offset that like 45 degrees and that won't be a problem. I was just doing this quickly for a demo. And then we just simply extrude that down along the outside surface. And we have these tiny little flat surfaces. The difference in height is like less than 1 millimeter or so. And for these sorts of things where you're just adding a little bit of material to a face, you can do that and it's not going to complain about it. On the physical model itself, you can barely even see them, but this lets you specify what the model looks like in Onshape, and then the 3D printer makes it happen. So these are almost 0 thickness. Like this is just taking it out from the surface, going out a couple millimeters for how wide I need the fins to be, and then taking it back down. So in terms of how far from the surface that edge actually is, it's tiny, it's nothing, but this is one of the times where that 1 millimeter minimum thickness for 3D printing, that doesn't matter here. And then I've got these flat surfaces, and that is where I can draw my fins on. So you could do basic rectangular fins like this, where you just draw your fin profile on the side and extrude it up. Or you could play around with more complicated designs for swept fins or all kinds of other things. Again, you can really do whatever you want for fins. We're going to be going with that looks about right for sizing and shaping of them. And this is really where we're going to be fairly experimental with it and have some fun, come up with some wacky ideas, and we'll see what flies well. When you have finished drawings or finished models, we want to export them for 3D printing. We're going to need an STL file for that. So on the side, you basically click select the part. Down the bottom here, I've got that selected. And then we're going to go to export and then give it a name. For when I'm going to get you guys to upload this to me, probably on a link on Discord, I would like it to have your name on that name. And then we can select the format being an STL file. The default there will be binary. The resolution's millimeters is good. If it's millimeters, it means that I won't accidentally make your thing this big. And things like the resolution being fine is a good idea for how small and detailed these parts are. And then we just export it and it'll download a file. Yep, that's pretty much all I have to say. It is about to be 2 o'clock, so I imagine some people have places they need to be. I will make sure that the resources to do all this stuff is available online. It'll be linked probably in general of the VEC Discord server. I can annoy everyone else who isn't doing that by spamming them with links. And yeah, I think that's everything I have. I'll say just like if you guys can finish designs maybe in the next week. Unless is anyone too worried about doing this in like week 6 or in the exam period? Does that terrify anyone? Probably about another 2-hour workshop, maybe a little quicker this time. It'll be physically building the fins, building the nose cone. Well, we'll have these 3D printed. We might have to take off some support material, and then it'll be, tying the lines together. We might be assembling parachutes and putting them together like this. We might have time for me to bring in some paint, and we'll paint them so they can look fun colors. I think with the number of people we have, it should be within budget that everyone gets their own parachute and everything. So hopefully we'll each have a complete rocket that you can take home, and then we'll find a sunny day to launch them all. Does anyone have any questions or anything else they want to say before I let you all go? Yes?
Can you put the slides on Discord?
I can indeed, and I have been recording this whole thing, and providing the 2-hour recording worked, I'll be uploading that too. Yes? That's all good. Yes? So it only fits one. What I want to do is if we have some rockets that fly really well and I have any budget left over, I might get some slightly bigger motors, and providing our launch site has the size and the wind requirements for it, because the higher you go up, the longer it takes to go back down, and the further the wind makes it go sideways in that time. That's how I nearly landed a rocket on State Highway 2. We'll try not to do that again. So we might fly it with some bigger motors, or we might fly them multiple times if we have extra motors. So maybe is the answer. Yes. Probably 1 to start with, and if we have leftovers or extras, we'll fly some more. We're also going to be flying on the A's mainly to begin with. And yeah, if there are some rockets that don't fly super well on an A, we probably don't want to put a bigger motor in it, because that's going to be even more exciting. Yeah, the rockets will take A's, B's, and some C's. The dimensions for the motor that I've designed this around are 18 by 70 millimeters. They will fit a lot of different SD's standard size black powder motors. For Estes, if you want to go any bigger, that's this manufacturer, you would have to go to a 24 millimeter motor. But there is a company called Quest and their motor line QJet, which are aluminium perchlorate composite propellant motors, which are a bit more expensive and much harder to light, but they provide a lot more impulse from the same mass of propellant. So I haven't tested fitting one of those motors into this, but theoretically it should fit, and those are substantially more powerful as well. So maybe in the future, if we've got some really nice flying rockets, we can do some big stuff with that. And if the rest of this workshop series goes well, next year, it's probably going to be next year by the time we're done, I would like to look at doing some more advanced rocketry stuff too. Yes. So the motor, you can see at the top of the motor, like throughout this thing, the propellant is only really like this part of it and a small one. The bigger ones, it takes up more space. But it has a delay section, and then it has just a pile of gunpowder. And that goes pop. It fills up the body tube with pressure. We've got some paper wadding that's going to be sitting below the parachute to make sure your parachute doesn't get burnt. And we have a pressurized body tube which pops the nose cone out and pulls the parachute out. This one's just been sitting on a shelf in my room for a while, so it's a little tangled up and probably wouldn't inflate super well. But yeah, it's just explosively pops the lid out, pulls out the parachute, and it hopefully descends nicely. Yeah. Other than that, any questions or anything?
Yeah, what's the rough timeline again?
Probably 2 to 3 weeks of getting everything 3D printed and ordered. I'll also probably put out like a form on the VEC Discord for where you guys can just tell me who you are and how to contact you. 1, so I have numbers of how many things to order, and 2, so when it's time to organize the next thing, I can send people emails to say, can you be here at this time? So
it's
yeah.
2 to 3 weeks until we have like the physical thing here.
Yeah.
So when do we have to have all this done by?
I'll say a week. So a week should be enough time that you guys can build some stuff around your busy schedules, because I know how that is. And then I can get everything ordered and printed and organizing the next workshop. Did you guys all have fun today? Fantastic. And I hope you learned a little bit too. And I will see you on the next time I do one of this. And I'll probably talk to you online.